Welcome to our second GRASP research overview. We have another jam-packed set of presentations for everyone. So I'm not going to dilly-dally. I am going to start by just doing a quick reminder to the presenters to first join via the Zoom. You guys should all have been made host capabilities. When you join, make sure you do not connect your audio, share your presentation through the share screen function. And then I'm the moderator, so I will give you guys, so everybody has about 5 minutes to do their presentation. We're going to allow for a minute of switch time. So I will count you guys down from 3, 2, 1, okay? If I show you 1, you better wrap out. Otherwise, I'm going to bring out that big hook and pull you off the stage, okay? So these are the presenters. And so hopefully everyone is here. If not, you've gotten your instructions. And without, okay, make sure I have everything I need. Okay, so for those of you who don't know me, I am Hsieh. I'm the GRASP Deputy Director. I'm also an Associate Professor in Mechanical Engineering and Applied Mechanics. So I'm gonna get to kick this off. So this is my lab group. You'll find some of them sitting here in the audience today. Now, a lot of the work that we do center around this concept of monitoring, using teams of robots to monitor large-scale, complex, and dynamic environments. And so a great example of this is the ocean. And so really the vision that we're sort of pushing for is that you really want to have the ability, the engine, the ocean is really this engine that drive a lot of the climate weather patterns around the entire globe. Now, part of the reason, so in many ways, doing ocean forecasting is important because you're interested in things like, when is a storm surge going to hit? What happens, when two hurricane tracks, what kind of intensity they might take on when they make landfall. If you had any kind of maritime disaster, whether it be because of an oil spill or you have, people on boats, right, which we've heard about, getting lost at sea, then being able to forecast, right, where those ocean currents are going to be really important for you to be able to do mitigation, to design your mitigation strategies and as well as your search and rescue strategy. But of course, our ability to do these kinds of predictions is very limited, and partly because we don't have a lot of good data. First of all, those of you, if you're not familiar with this, GPS does not penetrate the water. So if you're, neither does Wi-Fi. And so comms is very hard underwater and localization is very hard underwater. Even though the ocean is a fluid like the atmosphere, it actually, in terms of viscosity, it is an order of magnitude higher than air. So this actually makes the control problem very difficult, especially since most of the underwater vehicles you're operating are going to be underpowered. So given this, the idea that we are proposing is that you should be able to do some kind of a large-scale deployment, whether it's using a combination of satellite, aerial vehicles, surface vehicles, and underwater vehicles, and be able to strategically pick where you want to sample, right, in order to collect the most informative data from, that can be then incorporated into whatever ocean model that you're using, and be able to improve your prediction capabilities. So because of this, a lot of the work we do, we think about how do we coordinate teams of heterogeneous vehicles with heterogeneous mobility, sensing, and computational, and even communication capabilities, and how we send them out, right, and coordinate them so that they can do the best job of collecting the most important information. Given this, you have to also think about how do you fuse, right, these data that is not just fundamentally different resolution, both spatially as well as temporally, but also of different sensing modalities. And so if you're interested in constructing, depending on the types of processes you're interested in reconstructing, you would have to do both chemical sensing. There's some, physical properties like temperature, solidity, in addition to, maybe you're interested in understanding a particular ecosystem, right? So you're also thinking about things like counting wildlife, okay? And then, of course, we think about how do we do data-driven modeling, and not just of the vehicles themselves, but also of the processes that we're trying to estimate. And then a lot of this work I do with other faculty here at GRASP of thinking about how do we rethink, right, the mechanical design of our robotic systems, of our mobile sensors, that will then allow them to do a better job of leveraging, right, all these environmental forces that they're subject to improve their navigation, their control, and thinking about how can you leverage those forces to do better planning. So given this, we do a lot of adaptive sampling and environmental modeling, and we do this at different scales. So the movie that you're showing, those little lights that are changing colors, that is a bunch of little palm-sized autonomous boats that we have. We have a big water tank in the lab. And the idea here is, you want these boats to be able to go out and collect data. The environment is changing, which means where the most informative data is also changing over time. And so how do you allocate, right, sort of your sensing resources to these various tasks? And we don't just do stuff in the lab, we actually do stuff in the Schuylkill River. So this is a portion of the river that is immediately behind Pennovation. We also think about how do we use data? How do we leverage our physical knowledge of our systems, right? And then enable them to do better. And so how we enhance, right, the physics with data in order to do a better job of control. So this is like fresh off of the press, that video in the middle. These are two quadrotors flying within 2 body lengths of each other. This has never been done before, okay? To have 2 quadrotors flying one on top of the other, closely stacked. And part of this is because there's usually a lot of aerodynamic effects from the top quad, which makes this very hard. The video at the bottom here, that's the origami robot that Dr. Sung's group has made. And we're interested in understanding, right, how the deformation dynamics impacts its ability to be able to propel itself into the water, through the water. Okay. So we do some active flow learning. So these are sort of examples of really complex flows. Really, the main thing to look is that the movies on the left-hand side shows you the general dynamics. The learn features on the right-hand side, this is actually capturing sort of the topological information from a dynamical feature sense, okay? And then the last thing, I believe this is the last thing, is again, we go outside. So part of the reason why we're doing stuff in the Schuylkill River is because the Schuylkill River is this example of like tidally driven river. A lot of the drinking water from this area comes from a combination of Schuylkill and the Delaware. And so we're trying to understand how climate change and severe weather patterns now potentially impact, right, how the water quality changes over time. And so this is work that we're doing with Professor Douglas Jaramak, as well as Ugo Iloa from the Environmental and Earth Sciences Department. Okay, so next person in line, I'm going to pass the mic off to Dr. Figueroa. That was. Okay. I had 5 minutes. And so for the presenters, I'm just going to remind you to please students the microphone so that people online can hear.
All right. Hi, everyone. I'm Nadia Figueroa. And so I'm going to give you a quick overview of the type of work that we do in my lab, which focuses on developing human-centered robotic technologies. And in particular, what we focus on is developing computational tools for robots to fluidly and naturally interact with humans, to physically assist humans in everyday tasks. And one of the most important things is that we want robots to be adaptive. So we want robots that are interacting with humans or that are being deployed in human-centered environments to be able to adapt to changes on the environment, changes in the task, and even changes imposed by the human itself on the task. So one of the main thrusts in my lab is developing controllers for safe human-robot interaction. So as you can see in the video on the top left, this kind of like relies on having a very nice differentiable boundary function that represents the environment. So if you have something like that, that is being able to update online, for example, at 100 hertz, which depends on the perception frame rates, then we can plug that into our reactive controllers. And as you can see, the human can even kind of like play around and poke with the robots, and there will be no collision because our controllers have guarantees that there will be no collision as long as we have like this very nice differential boundary function. We have extended this currently to also safe navigation. So this video was taken in the 4th floor in GRASP, where you can see that now we have these reactive controllers working on differential drives, which is something quite difficult to do. And normally you need to do some like MPC and do some linearizations on these type of, for the kinematics of these robots. And we have now been able to do this. We can also do safe control directly in joint space. So if we have a boundary function that represents all the self-collision avoidance, all the self-collisions of a robot in 7-dimensional spaces, we even have examples with humanoids, and we have a representation of the human also, then we can have super reactive, running in real time, safe physical control. And so these videos that I showed right now, they are satisfying the safety requirements in terms of no collision, like no contact between human and robots. But sometimes we want the human to actually touch the robot, and 3 minutes left, or okay, yeah, good. We want to allow humans to touch the robots and physically perturb and move it around. So we also develop low-level controllers that are passive, that allow physical perturbations on the body of the robots, but that also guarantee that the human is not leading the robot into a self-collision or into a joint limit. So we can achieve all of these really cool behaviors because we take kind of like a different approach on how we control robots. So instead of doing the classical optimal control, planning time index trajectories, what we assume is that the human and the robot motions are driven by virtual autonomous dynamical systems of this form. Very simple first order differential equation. X can be the position, X dot can be the target, can be velocity, and X star is the target. So if we encode the motion policy of the robot as this type of dynamical system, then we can apply tools from control theory to ensure convergence of this motion policy, to ensure stability using Lyapunov theory. We can enforce safety through boundary-based invariance, and we can even apply tools from nonlinear control like contraction theory. So one of the cool things of representing motion policies this way is that we can have super adaptive and reactive control, right? Like we can formulate a policy for a robot to catch flying objects without any learning, without any GPU. This I did during my PhD in 2016 without any high data requirements or anything like that, just by nicely formulating a dynamical system. But that's a difficulty, right? Like how do you formulate these dynamical systems? Well, you don't have to. We can actually just learn them from data. And that's what we do in my lab. So we also do efficient learning where we give the robot a couple of physical demonstrations of the task, and then the robot learns this dynamical system policy. And now it's capable of deploying the policy and allowing the perturbations and still guaranteeing stability and convergence of the task. We have recently extended this to show that with a single demonstration, you can train one motion policy and then generalize to multiple instances of that same task by introducing geometric features of the task into the motion policy formulation. We have extended this to also learn cyclical motions, like you can see at the top. And also we have extended this to learn motions for the motion policies for the robot in full SE3 space using position for position and also quaternions for orientation. We have new work on composing these dynamical systems to do long horizon multi-step tasks that you can see here. And yeah, so we also have this, we couple now this type of controllers with estimation to do assistive control. And we're currently exploring how to use wearable sensors as well to predict forces and capability of the human in order to plug it into the controllers. So if any of you are interested in this type of work, I'm actually teaching a new course next semester. It's probably going to be MEME 6230, Learning and Control for Adaptive and Reactive Robots. It's based on a textbook that I wrote. This is a picture of my lab 2 years ago, which is when I birthed my lab. So this is how it started. This is how it's going. This is currently my lab, all of my collaborators, co-advisors. And if any of you are interested in research projects, you can go to that QR code and you'll find some projects for you. Right.
Thanks, come on. All right. Great. Hello, everyone. My name is Dinesh Jayaraman. I work broadly in robot learning, which is kind of an exciting little subdiscipline of robotics, but also kind of intersecting with computer vision and machine learning. And my lab is also a fairly young one. We're about 4 years old here at Penn. And today, my talk is titled How to Train Your Robot, because I'll be talking more broadly about the kinds of work that we do in my lab and some nice research highlights we've had over the last year. Okay, so I have kind of, I like thinking of robots as essentially devices that convert information about the world into some kind of physical work, right? And so if you kind of peer into a robot, what's going on then is a sequence of information processing computations that then somehow produce a command that can then be passed on to an actuator. And this is useful because what goes on in information processing is that at every layer of information processing, you're destroying information whether you like it or not. This is kind of a famous result in information theory from very early days. And so one way to kind of think about that then is that we are, at every stage of information processing, we are determining which information to retain and which information to discard, right? And so one way that I think about what we are trying to accomplish in the group is that rather than do what I think of as brute force robotics, where we're really trying to sense, remember, represent, predict, plan as much as possible, which is kind of in fashion these days, we are, and I'm trying to kind of think of it in a slightly different way. We want to think about kind of minimalist design of robotic control systems, where we are understanding trade-offs between task performance and the various resources that are really central to robotics, like information, compute, training data, and so on and so forth. Right? That's kind of like the high-level philosophy of what we are doing. And so one way to kind of formulate some of the questions that we're thinking about is that we're thinking about what does a robot learner need to sense and attend to at each stage of computation, all of those stages that I showed on the previous slide, in order to learn and perform a task. And how does the answer to that question then vary as a function of the kind of task that you're performing, the kind of agent, its morphology, its hardware capabilities, its learning phase, and so on and so forth. Right? And we've had some exciting results over the last several years in this direction. So to kind of like maybe zoom into that question, double click on it a little bit, the way that I think about this is that information is really generated in the world, in the environment, because there are processes happening in the environment that you're then trying to control. And so you can kind of broadly break up whatever information processing is happening into these 3 stages of observation, representation, and action, or maybe decision making. And at the observation stage, you're immediately faced with a choice. You're immediately faced with a choice of deciding which of the information that's kind of emerging in the environment needs to be looked at, needs to be sensed in order to gather task relevant observations. I'm sorry, I didn't see your 3 minutes. Okay, all right. And then which of the information then to retain in a representation, and then which of the information to attend to during learning and during planning, and so on and so forth. And broadly, most of the work that we do in the lab can be characterized as falling under 1 or 2 of these buckets, right? And we're hoping that all of this will lead to emergent capabilities in robots, like flexibilities in the ways that we can pre-train them, flexibilities in task specification, and flexibilities in resource allocation. So with that kind of like spiel about what the overall philosophy of the group is out of the way, let me show you some cool results that we've had in the last year or so. Perhaps the result that's gotten a lot of the most attention really is the series of results that my PhD student Jason Ma, working together with an undergrad, well, two undergrads actually, Will Liang and Sam Wang, have gotten really cool results doing sim-to-real RL. So you can imagine simulators like these, and then policies trained in them that then transfer onto real robots for tasks that are extremely difficult and also completely nonsensical. It's not like this task is something that people actually care about, but it's more a demonstration of the ability to perform a really, really difficult task that we wouldn't know how to synthesize a controller for other than this, right? So we're getting this quadruped to walk on a yoga ball. And you can see that we were very proud of this result. And Hangju here is actually walking these robots all around Penn campus on, on a leash, just to kind of, show off and gather and demonstrate our abilities on very in the wild kind of settings. The methods that we used in this project are very general. They're not very specific to this one task. And that's true of much of the work that we do in the lab. We try to develop very general methods. And so we've used them also for these kinds of, dexterous manipulation and for walking the quadruped and so on. And recently we have some results on getting this to cross an obstacle course as well. Okay. Here is an example from a different domain of robotics, manipulation. And in this case, we're also learning these skills in different ways. Rather than doing sim-to-real RL, we are providing demonstrations by teleoperating the robot and then learning to sequence skills that are trained through imitation learning to perform tasks that are quite challenging, both in terms of the dexterity required for each individual task, but also in terms of the sequence of skills that is being performed and how to chain that sequence of skills together, even if they might have been learned in different settings. So on the left, you see this kind of like multi-step napkin folding task. And on the right, you see kind of a toy eggplant preparation recipe that involves 5 steps that's being followed by this robot. Another kind of recent line of work that we are exploring in the lab is how over training we can kind of increase the sensing efficiency. And an example of that here is on the left, where we can kind of at training time actively perceive what the quality of the result is for whatever task the robot is learning, in this case, tightening a screw. And by actively perceiving it and learning to do that at first, we can use it to provide rewards then to boost policy learning. And on the right, what we have is an example of training sensing limited robots. Again, if you train them in the right way, what we've found is that sensing limited robots, in this case, completely blind robots, perform nearly as well as fully sensing enabled robots, vision enabled robots, as long as they are trained in the right ways. And this is kind of leading us towards answering those questions that I raised at the very beginning of the talk. With that, I think I'm out of time. So I'm going to hand off to the next speaker. Thank you.
Good afternoon, everybody. My name is Francis Sowande. I am a fourth-year MEME PhD student here at Penn, and I work at the Rehab Robotics Lab. So our lab involves, we take people from all different kinds of fields, bio, MEME, CS, even as far as neuroscience, and it's all for the purpose of bridging together our gap of robotics and sort of ideas and techniques of accessibility so we can provide accessible care for people with non-traumatic brain injury. So what this tends to look like is accessibility doesn't just mean money, it also means time. A common theme you're going to see today is the fact that sometimes the problem isn't necessarily that therapists aren't good at their job, it's that there's not enough therapists for the amount of people that need care. So what we're trying to do is provide them with tools, take the really fancy robotics knowledge that we know to adapt these things to just make their lives easier and make the therapy process easier for the patients as well. We work with a variety of people all over the world, even internationally. I believe Dr. Johnson just got back from Botswana because we work with the Princess Mariana Hospital in Botswana, and we actively apply some of our projects there. The first project I'm going to talk about is rehab cares. And like I said, a big issue in the space of therapy and rehabilitation is that there's just not enough therapists for the amount of people that need care. So the idea behind this project was how many patients can we see at one time with one therapist? So this was a system where we have multiple sort of nodes and check-in points where Most people can see therapy at one time, but we found that the star of this system was really the TheraDrive, which is a 1 degree of freedom robotic arm for upper limb rehabilitation and assessment. So the TheraDrive, as you can see here, comes with a variety of games. Here, you can see the GIF with the white and the green arrow. It's a task tracking game. The orientation of this robot can also be changed to sort of engage, make it a cognitively challenging task as well. And we don't look at this, we look at this primarily through for the application of stroke being one of the most common impairments in the world in general, but we also look at this relative to other things, including aging, HIV, and even sickle cell. From the TheraDrive, we've had some more projects come out of this, one including the TheraDiad. And as you can see here, we have 2 of these 1 degree of freedom robots connected to each other haptically. And so, you know, there's spring constants and dampening constants. And what this does is that it allows us to see how people working together can make, you know, rehabilitative task improvements. You know, do you want somebody working with somebody that's better than them, worse than them, a family member? And so really exploring how these things can help. Also, we're looking at how sort of what sensing we can use to get information from people. So we've looked at EMGs, IMUs, ultrasound, and contact point sensing just to see how much information we can collect, because not only is sort of applying care difficult, but also having sufficient resources to see how impaired somebody is also a difficult task. And another project that we have is the BiAdler. So the BiAdler involves an active robotic arm and a passive robotic arm. And we have this because it's for bilateral impairment. Like I mentioned, stroke is one of the most common impairments in the world, and it tends to affect one side more than the other. So we have the passive arm for collecting data from the sort of the less impaired arm, and the active arm thus performing movements that are necessary to compensate for this. Here is the PandaGym project. This is the project that I work on, so it's my favorite to talk about. And so in this project, like I mentioned, a big issue is that it's hard to, for a lot of clinical testing, you know, it's quantitative. We want sort of, it's qualitative. We want quantitative metrics. And so this project's all about collecting quantitative data on infants 1 to 6 months, including data from cameras, computer vision, a pressure mat, as well as a custom sensitive toy. From this project, we have the Lossy Sensory Infant Simulator. The Lossy sensor is using fiber optic cables as well as 3D printed lattice structures, and the way the light changes as these lattice structures bend to measure force. And so we've implemented this into a toy, and we were able to see that not only could we collect this data, but we could also kind of classify the kind of interaction. Next, we have the infant simulator. I did make that. And we built this robot for the purpose of collecting data that we can't normally ask babies to do. Finally, I'm going to talk about Flow, and Flow is a telepresence social robot for the purpose of, again, helping people in therapy. It collects data with cameras, and it plays games. It can play Simon Says, and Flow has a friendly face, and we're currently working on making it more dexterous and more autonomous. We have many, many projects that I didn't talk about today, including looking at how brain scans can tell us about impairment. And if you're ever interested, please feel free to reach out to any of us. Thank you so much.
All right. Hey, everyone. My name is Anish. Good afternoon and welcome to GRASP to all of the new students here. Unfortunately, I'm not Vijay Kumar, but I am his PhD student, so I'll be filling in for him today. So if at any point you have any questions, you can check out kumarrobotics.org. We do our best to update it with students and projects, but as always, you should reach out to PhD students if you're interested in research. So here's a list of all the PhD students. I think we have somewhere around 18. A lot of us sit permanently in Pennovation. Some of us switch back and forth. So you might see us in GRASP, shuttling in and out. Most of our robotics, like actual robotics hardware experiments for ground robots, aerial vehicles, all happen in Pennovation. So maybe you've seen that in the welcome events. Okay, so I'll start off with one of the biggest themes in our lab, which is autonomy with swap constraints. So swap constraints refers to size, weight, and power limited robots. And so these are usually very small aerial vehicles. We have 3 or 4 different kinds of them, as you see on the top, ranging from like 200 to 400 grams. And we've done in the past and ongoing a bunch of swarm robotics tasks with these. So the example shown in the video is this graph convolution network based method for swarm navigation. And so for most of the projects I'm showing you, I think if not all of them, all of the computation is done on board, even on a bunch of these tiny drones. So they have custom made or off the shelf computers on board that do all the computation and communicate between the robots. Okay, here's another example of a project where this one robot is entering a new environment that it's not seen before, and using vision sensors, it's mapping out the environment and choosing where to explore to fill out the map that you see in the top left. Okay, I'll dive a little bit very briefly into my specific research. So I'm very interested in agile robotics. And so at the time I'm working on quad rotors. And I'm inspired by how humans can use just the FPV point of view. So if you've seen like these humans piloting quad rotors at very high speeds through indoor and outdoor environments with this these goggles, which is the FPV viewpoint through the quad rotor's eyes. And so we can see that humans are able to pilot these drones extremely fast through novel environments. And so I'm trying to endow autonomous quadrotors with similar kinds of abilities. So one route in which we've done this is using depth images, which there's a lot of prior work for. And we train a simulation-based policy that uses an attention-based vision transformer model to do end-to-end control from depth images to like direct to velocity control of the robot. And we were able to zero shot deploy this model in the real world and observe that it has quite agile behaviors, like from 4 all the way up to 7 meters per second indoors. And then another one of my passions is using event-based cameras or neuromorphic cameras that mimic the human eye or the primate visual system. So how humans perceive dynamic versus static information in their optic nerve system. And so on the top of this drone, on the bottom left of the screen, there's an event camera, which is graciously offered to us by Costas to use. And we're able to show multi-obstacle dodging indoors and outdoors. And what the event stream actually looks like is this red and blue video in the bottom right, which we then distill down to a predicted depth and then to control commands. I'll go ahead and skip through the rest of the videos for the sake of time. Yeah. Okay, so another big thrust in our lab is agricultural robotics, where we're interested in crop monitoring and also measuring the carbon biomass of a forest and mapping out the forest in quite a lot of detail. So previously I was presenting a lot of the small robotics platforms. This is one of the larger Falcon 4 UAV platforms, which is fully custom built in our lab. It has a 3D LiDAR, cameras, and IMU on board. And with the onboard computers and sensors, coupled with our open source autonomy stack that you can find on GitHub, we're able to perform real-time metric semantic SLAM and robustly and safely navigate through a dense forest. Let me play this video. And so in the video, you can see that the Falcon 4 UAV is executing a fully autonomous mission in this under canopy forest environment. And there's a GPS denied environment, right? Because the dense canopy of the trees is blocking satellite GPS signals. The system design is on the bottom left. And then as I mentioned, we do a lot of crop monitoring and there's a larger project between many universities on agricultural robotics. So that's represented on the bottom right. And finally, we do a lot of heterogeneous multi-robotic team problems. And so multiple students in the lab are working on this. One such example is where we task robotic teams with intuitive specifications specified in language. So for example, a user might tell the robotic team that there was just a heavy storm, for example. We need to triage the area and search for humans who might be in need of help. And so this robotic team then can automatically decompose the task into subtasks, accounting for different robot capabilities. So as you can see in the picture, there might be multiple types of UGVs, so ground vehicles, with different capabilities operating in the scene with a UAV. And then feedback is given back to the user, and then the user can update the task. And so we're exploring this whole language specification and autonomous multi-robot team, the combination of these ideas. So currently we're doing single agents, but we're scaling up to multi-agent. And so yeah, emergency response and logistics is a big application of these. So yeah, as I mentioned, if you have any questions about research or interested in research opportunities, feel free to reach out to some of the PhD students. Here's a picture of Lab and Friends. Thank you.
Good. So hello, everybody. My name is Antonio, and I'm probably the latest arrived PI in the GRASP lab. Arrived here like essentially 1 month ago. Very excited to be here to see many new faces and so many young faces ready to hopefully revolutionize robotics. My talk today is not going to be about fancy results and cool videos, as it usually is. But it's rather going to be about philosophy and like about the philosophy, what is going to be the philosophy and the main research emphasis of my labs. As Dinesh, I work in robot learning. And one thing that really interests me is having an holistic approach to physical intelligence. Let me give you a little bit more details on this. So I was thinking how to best present my research philosophy. And really, I was thinking for a week. And then last Saturday, I was at a PhD graduation party, and I had this conversation with this guy. He told me, oh, what are you working on? And I'm like, robotics. He's like, oh, cool. Which part of robotics? And like, I mean, what do you mean? I mean, robotics is robotics. It's like, well, mapping, state estimation, planning, control. You know, I'm like very confused, like, you know, what are you talking about? And in that moment, I understood what is one of the main problems of robotics, which is the fact that very often as roboticists, we miss the forest for the trees. Like suppose that, for example, you want to, like you have this ambitious goal of creating, I don't know, like a robot for forest monitoring, right? So what do? Well, you build the robots, you have some sensors that observe your, like your environment. You pass those sensors into an estimation module, a lot of pain, but you know, you succeed. Then you pass this in a planning module, again, like a lot of pain. And well, planning, you're almost done. Okay, now you have to do control. And at the end of this, maybe if you're lucky, you can do actions. And I'm like generous here, like there might be like others, many blocks from actions there. Now, this is a problem. This is a problem because this is not going to be a very exhausting process. Like maybe by the time you're done this, like, you know, you completely forgot the original problem you were working in. But this also has the problem that more often than not, what happens is that you make some hardcore decision that don't work well downstream, right? So like, for example, you might have designed your estimation module to like do one thing, estimate the pose of the robot. But what if like you need more information from the environment? You have to, I don't know, you need the color of the foliage or the type of the trees. Here we go, like you'll have to restart from scratch. That's why what my lab is going to focus on is a much more holistic approach, which, you know, like takes sensor observation directly to actions and could, in theory, again, empower engineers to focus on the high-level problems, not on some, you know, high-level, low decision-making. So this is going to be research focus number one. Let's go on the second of my research focus. And for this, thank you, I'm going to go back on of a couple of years and move to like research in NLP. Okay, this is how, maybe many of you don't even remember, but this is how NLP research looked like in the pre-LLM era, where thousands of tasks. I mean, many of those I never heard them before, like, translation, program execution, text categorization. Like essentially it was a match between expert researcher who could come up with the weirdest task name. Now, and how would you do this? Well, the traditional ML paradigm, right? You create an algorithm, you design some task, you collect some data, you train a separate model, you get 0.5% better than your peers. Boom, you are like, that's enough. Now, some of you might even remember there was like the time where the entire NLP community was like just trying to put BERT features on every task. Like all of this work now is completely obsolete, right? Why? Well, because there was a paradigm shift with LLM research in which people like really understood that we have to move away from expert-defined tasks where some, like engineers, researchers sit down in their research silos and come up with some ideas of task to user-defined task, but rather focusing more on like a general unsupervised way of like building knowledge. This is kind of what enabled like the big jump in NLP and machine learning and computer vision research. And I think this is, again, what my lab will focus on, like try to repeat those things in our robotic settings. Of course, you might wonder, well, why are you bothering, right? Like, we know how that works. Like, let's just apply straight what happened in NLP to robotics. But we can't do this. Like, this is actually a very interesting and exciting research problem for a set of reasons that many of you, I guess you already heard. Like, well, we are controlling perception-based safety critical system, right? Where a success rate of 90% is not enough, right? I don't want only 90% of my task to be done. Like, has to be complete. We also don't have no widespread data source, like we have to come up with something. And we have limited compute of the edge. I mean, like I have problems doing sometimes my Zoom meeting on my laptop. How can I hope that my robot will have access to like very fast connection all the time? There are going to be some, of course, like this is a general problem. The main tool that my lab is going to investigate is this thing called sim-to-real transfer, in which we train system on a simplified model of reality and we apply them on the real world. We've demonstrated this for many things. And one of the reasons why this is a general problem is the fact that, you can cast this problem for like even more general setting. Like, for example, in this paper that we published just yesterday on Archive, we cast the problem of learning from videos in a sim-to-real problem, and it did quite well. And all the thing that like makes me really excited is the fact that we can call LLMs or VLMs a simulated model of reality. So with high probability, we might be able like to do something like this, to use them to train our system, like to leverage our knowledge and then apply them in the real world. And overall, that's it. If you're excited about this kind of research, please get in touch. And yeah, we're always looking for excited people to working with. And with this, that's all. Thank you very much.
Okay. Hello, everybody. My name is Bruce Lee. I'm a fifth-year student with Nikolai Matni, and I'm presenting on behalf of the Matni Group. You can find our website right here, where you can find information about our PhD students and ongoing projects. So please go there and ask any students if you have further questions. Okay. So at a high level, our group is motivated by the fact that machine learning methods are very convincingly being applied to a lot of real-world complex decision-making tasks. Okay, so we have self-driving cars that are performing adequately well, Boston Dynamics robots that are capable of doing parkour, doing flips, and an OpenAI hand that can do quite convincing in-hand manipulation. Okay, but at the same time, these methods that produce the videos we saw on the previous slide tend not to be very reliable. So some of these videos might be a bit outdated, but we have an example of an Uber running a red light, a Boston Dynamics robot destroying an office environment, and a Majoko simulation that learns very unnatural and quite fragile trajectories. Okay, so motivated by this challenge, the broad approach taken by our group is to try to bridge the gap between classical dynamics and control methods, where we have often guarantees of robustness, we have guarantees of stability, with state-of-the-art learning methods where we saw those demonstrations on the previous slide, but they tend not to be very reliable. Okay, so with this broad approach in mind, the few main thrusts of our group are firstly in the foundations of control and machine learning, and in particular at their intersection. So in this thrust, we tend to look at simplified, analytically tractable situations from model-based reinforcement learning, from imitation learning, or from decentralized control. And we try to rigorously understand what are efficient algorithms and what are optimal algorithms in those settings. And in these settings, we're able to make some guarantees about the performance that the algorithm achieves on this task in terms of the properties of the dynamical system we're considering. Okay. And additionally, this gives us some insight into how to mitigate issues like distribution shift and imitation learning. Okay, so from this main thrust of our lab, we have a couple other big thrusts. One is in perception-based control, where there's a lot of different directions going on. Some are using some of the robust control methods in perception-based control, but others are using new types of sensors like event cameras to try to incorporate those into the decision-making loop. Okay, so this is some of the work done by Anish that you actually saw a couple of presentations ago. And one of the other main thrusts, also motivated by this foundational study, is in layered control architectures. So here, the main motivating reason for the study is that, well, modular approaches tend to be very effective in practice. They're the reliable approaches we tend to use. The end-to-end approaches that we saw in the previous presentation also have demonstrated very impressive performance. So we're trying to, in some way, bridge the gap and still use the modular approaches to get the guarantees and convenience that modularity brings, but also get some of the enhanced performance that end-to-end approaches tend to bring. So in particular, on the left, we have kind of a modular approach where we separated trajectory optimization and low-level control. And on the right, we've learned some tracking cost to incorporate the low-level control difficulty into the trajectory design. Okay, so with the last couple minutes, I just want to go into a little bit more detail in these layered control architectures, because I think they're a very good mapping of the philosophy of our research group. So this is work by Anusha, and it's joint with the Kumar Lab and some of his students. But the main idea here is that we've identified this problem where a naive decomposition into trajectory optimization and low-level control actually can be quite bad, as we saw on the left above. And the solution is to learn some sort of penalty on the tracking cost. The nice part about this, and where it ties in nicely with the foundational motivation of our lab, is that it's backed by rigorous theory in some simplified settings. Okay, so in particular, this rigorous theory gives us some indication of why this method on the right actually performs better. All right, so the high-level approach here is that in simulation, you can learn a tracking cost for particular trajectories, and this can be incorporated at inference time when deployed on real hardware. Okay, so just to end off, I'll just show what this looks like. So on the left, we have the baseline approach that uses modular trajectory optimization. And on the right, we incorporate the low-level tracking cost into the trajectory optimization. So in the left, it crashed, but in the right, by incorporating this information about the low-level control into the trajectory optimization, we're able to succeed and avoid crashing. Okay, so to conclude, I'd just like to say that these are the stable heroes of our group, which is called the Unstable Zeros. So it consists of about, I think, 9 PhD students, a postdoc, and several alumni. So thank you.
Okay. Good morning. My name's Lucas Hansen. I'm a PhD student working in the Miskin group. Today I'm going to talk to you about our work on micro-robotics. So we design and build micro-robots in the Miskin group. This is an example of one such robot. You see here that it's walking around on this silicon chip. And all of our robots share a few main properties. So generally they're smaller or about the size of a human hair. The biggest ones we make are just at the resolution limit of human vision. They live in solution environments in liquid phase, and they achieve actuation through electrochemical interactions. And these electrochemical interactions are powered and controlled by onboard CMOS electronics. In this case, this robot is being powered and controlled by very simple electronics. These are just solar cells that it uses to actuate the legs in response to laser light illuminated on a desired solar cell. But there's two main reasons that we build robots this way, electronically integrated robots this way, is that you can make more complex circuits. So this is a robot designed by my colleague Michael Reynolds. That's a hexapod, and on board this robot is not just the circuits needed for power and control, but also programmability. So he can shine light at this robot to communicate instructions, to tell it to utilize a certain gait pattern in order to walk in a preferred way. So the other thing that's really attractive about micro-robotics is that you can build them massively in parallel. So in this video, I'm just going to show a few dozen robots being released from our fabrication substrate. But in principle, you can produce thousands or tens of thousands of robots in a single fabrication run on a 4-inch wafer. So what I work on broadly in the Miskin group is trying to develop new locomotion strategies to expand the solution environments and mission objectives, I guess, that our robots can use. And so this is a device that I designed with my colleague, Will Reinhardt, that instead of using legs to locomote, it uses electric fields essentially to propel itself to solution. So this device, again, consists only of photovoltaics, no programmable electronics. But what it does is it uses the light that it harvests from these photovoltaics to drive electrochemical reactions at these two electrodes on either side of the device. And these electrochemical reactions result in a flow of current through the solution surrounding the robot, which in turn corresponds to being an electric field. And this electric field can exert forces on ions in solution and on surfaces around the robot to generate propulsion. So I'm going to show this video here of me with my pipette putting a robot into solution. You can see there it moves around when we shine light. And what's really cool about these devices is we found that the amount of light shining on the robot essentially corresponds to the speed that it travels at. So if we take two of these motors or robots and we stick them together with a crossbar, you can create a differential drive robot. So by shining the same amount of light on both of them, the robot will travel straight. But if you asymmetrize, you can cause it to turn. And so we came up with an automated system of doing this, and we get our robots to navigate along these waypoints here. So this one is going along in a figure 8 pattern. It also allows us to address specific robots to go in certain paths in response to what other robots around them are doing. So here they're sort of traveling along and waiting for their friends to catch up as they reach these waypoints. We can even do swarming behavior where we have individual robots act as a waypoint for robots further back in the chain. So they're sort of navigating along this conga line. But as I mentioned before, right, the real value here is that we can integrate more complex electronics. So this is the work that my colleague Maya Lassiter has been doing the past couple of years, is using this more sophisticated chip designed by our colleagues at University of Michigan, the Blau group, where she can actually program it to use the same actuation mechanism that I showed in the previous slide, but arbitrarily decide which electrode is going to output current and which electrode is going to take in current, in this way directing the electric field to create different movement strategies. So here it's just moving forward, sort of in the same way that I showed before. You can also get it to move side to side and turn, depending on what programming you use. So this is just one example of what we do in the Miskin group. I'm really interested in this topic of micro-robotic matter, but we're also interested in lots of different things: adaptable metamaterials, reconfigurable biosensors, and sort of the canonical application for micro-robots of micro-robotics in medicine. So if you're interested, check out the website, email Mark or any of the grad students, and let us know. Thanks.
All right. Hey, everyone. Hopefully you can hear me well. My name is Zach. I'm a second year ESC PhD in Georgia's group, also advised by Vijay Kumar. Here is an overview of the group's current members. Fairly large group backgrounds are mostly ESC, some computer science and applied math. And what I'll do is briefly touch on some of the current topics in the group and then dive into the last one, the bottom right one, a bit more. And so a few recent topics that we've been looking on, broadly learning for control. It's a lot of work in collaboration with Dick Matni's group, and so this will be similar to what Bruce just shared, but it's really trying to look at theoretical limits of if you have a controller or a system that you're trying to collect data and learn for, what can you say about the amount of data required for that? How do you most efficiently acquire that data? Once you have some controller, what can you say about robustness, generalization properties like that? There is work on multi-robot coordination. So how do you get teams of robots to work together in a distributed fashion? So something that you could apply in the field without infrastructure. The project shown here is using a lot of graph neural networks. So we have a team of UAVs. We model it as a communication graph and then learn controllers on that. There's work on safety for planning. Project here is looking at closed loop systems. So if you have a procession system, how do you put confidence bounds on that? So intuitively, if you have confident predictions, you can plan a little more aggressively. If confidence bounds are looser, you might want to be a little more cautious. And then newer line of research is in language-driven planning, and this is what I'll dive into a little bit more. So I've sketched out the problem domain here. We're looking at tasks like logistics or disaster response. There's a user who you really just want to task a robot with some simple mission specified in natural language. And so the tasks here are inherently high level. Goals are implied, and this is in contrast to a lot of current or a lot of tasking paradigms where you need to explicitly provide goals or semantics to a robot. Here we're looking at partially known environments, and so you might have priors from satellite imagery or UAVs, but you need a lot of real-time exploration, and it's very unstructured settings. So the robot needs to navigate clutter in a large-scale environment. And so really these three pieces of the problem make it a challenging and interesting space for us to look at. Mostly I'll be playing a short demo, but I wanted to sketch out our approach just to show you what's going on. We have a planner composed of a language model that will take a user-defined task, decompose it into a set of behaviors that are coming from some library and action set that include active sensing, mobility, and user interaction. This plan is validated online, so language models or foundation models are prone to hallucinate, and so we have module to automatically prevent unsafe actions from being realized. And then online, this is realized, this interfaces with some mapper, like what I've shown in the top left, and then it'll send control authority to robots. So we're considering mobile robots right now. We have a Jackal UAV or UGV on the top right. We're looking at extensions to air vehicles and looking at multi-robot teaming applications too. Okay, so here's what things look like now, just to orient what's going on. So we'll have a prior from a UAV that is in the map that's shown in the top left. So this is Pennovation reconstruction of the area. Have a user in this scenario, it's a disaster response task. So we're saying there's a chemical spill, triage the region, and we want to make everything task driven. So what the robot's going to do is infer what it should be looking for and then set exploration goals and realize those. And so this video is sped up quite a bit. It's maybe 20 minutes condensed into a minute and a half, but hopefully you can see that the planner is inferring if the map's built from a UAV, the regions that are covered are inside buildings and under trees. So it's looking to explore inside the building. It infers that it needs to find if it's a chemical spill, barrels and people for triaging. And so it will do that, detect that, and then actively map out the environment in real time, update its plan. Again, the priors are coming from remote sensing, and so they're not perfectly registered. You'll see the priors are taking it through some trees, and so on board it will recognize obstacles. It will avoid them and eventually cover relevant regions for this mission. Again, a bit more exploration, and then another nice property of this is it's all interactive. And so real time, the user can task the planner, query more information about the scene, or retask the planner online. And that, I believe, is the end of this. Thanks so much. Happy to answer any questions that you have later.
Hello, everyone. I'm Huzheng from Jianbo's lab. I also work with Hsieh. Today, I want to share with you a Python package we have built. It's called Uncard PyTorch. So we use this package to visualize model features. Like this video is visualizing SAM image encoder features. The deal is we want the color to be aligned across all the image frames. Like the body is always reddish across all the frames, and the ground is always green. So, and color means distance, like the body and hands, they are reddish color, and ground and grass, they are bluish color, which is bluish is far away from reddish. And the challenge is to make this color align across many image frames. We have to solve this normalized cut on the concatenation of all the image frames. That is millions of pixels and nodes. So we made this new Nystrom approximation algorithm for solving large scale graph cuts, and it runs really fast. We have a live demo running on Hugging Face. Let me just run a different, run a clip model on this slot, and run a Dino on this slot, and run a SAM on this slot. So by the way, in this demo, we have implemented many data sets you can play with and many models you can play with. Okay, it should be run under a few seconds. Somehow this Dino runs faster than. Okay, now we have the results. You can see how this model features looks like. And again, the deal is we want the color to be aligned across many image frames, like how the clothes is always in this bluish color and head is always in this brownish color. Somehow this gets stuck. That's good. And last thing I want to show you is with the help of green encoding task, we can make the color align not only across many image frames, but also across different model and layers. So this way we can see different models and learn similar representation. Like in this example, on clip layer 5, this person is in this dark bluish color, and that happened also on Dino and on MAE. And we can also see from left to right how the model feature is computed from layer 0 to layer final layer. Okay, thank you. And if you are interested, please check out the Python package Uncard PyTorch.
Hi, everyone. I'm Kate. I'm a PhD student also advised by Jianbo Hsieh. And today I'll talk about some of my recent and ongoing projects. So here, the first project is on amodal completion, where the goal is to try to complete occluded objects. So here I have an image of a cow, and you can kind of imagine like what the rest of this cow might look like, even though it's hiding behind these two other cows on the left and right. But what if we get a computer to try to do the same task? Well, oftentimes what we'll find is that because these computer vision models like Stable Diffusion, they've seen a lot of everyday images. Oftentimes they're going to try to insert other animals like other cows into the same image. And so how can we overcome this? We can kind of think of this as like cows are very social animals. And so oftentimes if we see a cow on a grassy field, there's probably going to be other cows. But what if we try to move this cow into the city, into like maybe like concrete in the background, right? It's pretty rare to see a cow in Philly. And it's probably even more rare to see multiple cows. So that's what we're trying to do here. So let's change the image context. And instead of putting this occluded cow on a grassy field, we're going to move it onto this gray background. And once we have it on this gray background, we're then able to run this diffusion process and slowly form the shape of this cow. But as you can see in this noisy image, like we're still diffusing this cow onto the gray background. But you might wonder, like, how can we put this cow back on the grassy field? And so what we're doing here is we're not only running diffusion process on the cow on this gray background, but also on this grassy field. And then at some point in the intermediate process, we can then identify the features corresponding to this cow and segment out the cow and put it back on the noisy image of the grassy field. So that's what we have here on the right. And afterwards, we can then complete the cow. And you can kind of compare this with what you might have imagined from the very first slide of what this cow could look like. And so here are some more examples. And we can also show like diverse completions for the same object. And one of the ongoing projects that I'm working on is oftentimes we've probably taken many selfie photos, but how can we convert those selfie photos into portrait photos of ourselves? And you can kind of think there's probably multiple challenges here. So here are some of the current results, but as you can see, like sometimes it's still hard to preserve the facial identity of the person, or maybe like the position of the arms are really hard to remove. So if you're interested in projects like these, like feel free to reach out. I'm happy to talk. Yeah. Thank you.
René, I think we're gonna let Marc go first since he's here, and then we'll put you, I'm just gonna put you at the end. Is that okay?
Okay. Thanks.
Okay, great. Marc.
Okay. Well, hello. I'm Marc. I'm kind of a relatively new member of GRASP. You might say, based on this graph, a spy from the NLP group, working in trying to get in for computer vision and robotics. My interests are kind of at the intersection, mostly of computer vision and natural language processing, interested in these kinds of questions. So, how do we get, machines to talk about just about anything in a reasonable way, intelligently, maybe even specialized topics? How do we get machines to see as much as humans can see in every kind of domain? And how do we do all of this without actually implicitly imbuing our models with kind of unwanted human norms? So one kind of like big theme in my lab right now is centered around this long statement. In kind of thinking about whether or not coupling behavior and language can give us new properties in models while kind of keeping them highly performant. And so my kind of idea for this is it's got to be true, in part because I believe language is one of our superpowers, and it kind of enables us to get away from evolution in some ways and actually learn from generation to generation and pass that on. And so there should be lots of information in language, and now's a good time to get it because language models have actually made it extremely accessible. So I'm going to just give you a few examples of this, not really trying to explicitly justify it, but just say it's possible, and I'll show you. So one project that we've been working on, this is with Yue Yang in a collaboration at AI2 called Holodeck. If you guys are Star Trek fans, you know what that is. The idea is that maybe what we can do is create a promptable simulator, okay? And so in that way, create environments for agents to train in, okay, dynamically, and zero shot, enable adaptation if we don't have data for new environments. And the kind of idea here is really to leverage the fact that language models know a lot about how environments should be laid out, okay, and connect that knowledge to an explicit, engine. Okay. And so this is something that UA has done. Actually whatever kind of environments you want, you can get them. So here's a few examples, 3 professor offices connected to a long hallway. The professor in an office 1 is a fan of Star Wars. This is CCB, who's an NLP professor. And so we can generate these kinds of environments and then train agents in these environments so that they can generalize to places they've never been. So this is something we've been doing. Another example of this kind of like controllability from language. This is a project with Lingji, who's also in GRASP. The idea is essentially to mediate motions with representations from language, okay, of how parts of people should move, and explicitly have generators model these pieces. And if they're in natural language in the guts of the generator, what you can do is actually get editable animations, right? And so essentially you can edit the language in the guts of the generator using language models in kind of consistent ways and actually get consistent edits to motions. So this is something we did at ECCV. Another example, this is probably, potentially a favorite of mine right now, is thinking about medical imaging. And so this is a collaboration with James G in radiology. The kind of idea is addressing the problem of transfer between hospital. So one kind of issue is that often models trained in one particular setting don't generalize to another, even if it's the same problem. So one example of this is COVID-19. This is like real fact. So, during the pandemic, it would have been useful to get training data, say, in New York and apply it in San Francisco. This was actually not possible. And kind of the reason for this is actually this giant gap in performance once you move from one hospital to another. And so part of what we've been doing is addressing this using a kind of really, language and thinking about how to extract principles of analyzing medical images from documents in PubMed, okay, using language models to actually structure recognition directly in the medical setting. And this can actually give you kind of much, much more robust systems because you are being consistent with clinical practice that's expressed in documents. And so this is the kind of thing we've been doing, and it works quite a bit better. And if you're excited about these things, reach out, in particular kind of, language in grounded settings. I'm kind of game to talk about whatever you're interested in. All right, thanks.
Okay, we have one more speaker, last but definitely not least. Renee, if you want to share your screen. And Mark, oh, there we go, perfect. And then I'm gonna try and bring Renee up here on the screen. There we go. Now we can, perfect. So Renee, whenever you want to start.
Perfect. Can you hear me? Hello? Can you hear
Go
me?
ahead. Yep.
Okay, great. So my name is René. I'm a faculty in the departments of radiology in the School of Medicine, as well as electrical and systems engineering in the School of Engineering. Here are some pictures of my students. I just moved from Hopkins not too long ago. So on the top left is a picture of the students in my house, and then after they moved to Penn. I have a very diverse and large group of students from many departments, including applied math and computational science, biomedical engineering. Most of my students are actually in computer and information science, but a few also in electrical and systems engineering. So the research areas within my lab are very broad, and I would like to highlight three broad areas, really: machine learning, computer vision, and biomedical data science. Within machine learning, we work on a very diverse set of topics, but I think the main theme of the lab these days is understanding the mathematical foundations of representation learning and deep learning. Within computer vision, we do a lot of work on understanding humans, recognizing actions. And within biomedical data science, we work on a rich variety of applications ranging from autism to Tourette syndrome, rehabilitation therapy, radiology. To begin with, maybe some example projects, I would say one of them that we've worked for a very long time, it's really the question of learning good representations of data in an unsupervised manner. And we use a lot of techniques from dimensionality reduction, clustering, unions of low-dimensional subspaces. And these days, this is, of course, integrated with techniques for unsupervised learning that come from the deep learning community. And we apply those techniques to diverse data sets, but primarily, I think, computer vision, images, and videos is what at the center. But we've moved these days into representations that involve both vision and language. On the theory front, for many years, we've worked on understanding the fundamental underpinnings of learning deep networks. And this involves work in optimization, understanding global optimality, work on dynamical systems, understanding the learning dynamics of algorithms, particularly in cases where networks are really big and over-parameterized, and having theorems of convergence rates, and guarantees of optimality and robustness for the representations that are learned from data. A big theme in my lab these days has been trustworthy and explainable AI, particularly focused on the areas of robustness and explainability. And this is driven by many applications, but one of them is radiology, trying to make diagnosis with explanations for the diagnosis. But one concrete example is a framework we've recently developed called Semantic Information Pursuit that aims to do explainability in a way that is semantic and by design, by having AI algorithms ask a sequence of questions, like in this case, questions about attributes of birds in an image, and then producing the class of the object based exclusively on this sequence of questions and answers. This requires a lot of work in computer vision and the integration of large language models and large computer vision models for doing scene interpretation, object detection, visual question answering, which are sort of core computer vision techniques. And we have a couple of students working on these problems.
So René, we have to wrap up.
Yes.
So I'll give you one more minute to wrap up.
Yes. Let me just wrap up with the last slide on a rich variety of biomedical applications that we're working on. And perhaps I'll highlight only one of them. We worked for a couple of years on developing a new blood tests where the idea is to take a drop of blood, then pass that drop of blood through a microfluidic device, image it, and then be able to produce counts of red blood cells, white blood cells, to produce the final blood tests. let me skip the rest and just say thank you very much.
Thank you. Okay, so thanks again to everyone who presented. There's pizza out back. So just so you guys know, we should clear the room because there is another class coming in. Thanks again.